Okay, let's start with Egoroff's theorem. Assume E has finite measure and when Fn be a sequence of measurable functions on E that converges pointwise on E to the real valued function f. Then for each epsilon greater than 0, there is a closed set f containing E for which Fn tends to f uniformly on f and measure of E minus f is less than epsilon. That is what we have to show here. See, given that E has a finite measure and Fn is a sequence of measurable function on E that converges pointwise on E. Okay. Fn is a sequence of measurable function which converges pointwise on E to the real valued function f. Okay. Then what we have to show? Then for each epsilon greater than 0, there is a closed set. There exists closed set f containing E for which Fn tends to f uniformly on f and measure of E minus f is less than epsilon. To see this theorem, first we see the lemma, which is useful to write the proof of that Egoroff's theorem. Okay, so for lemma is under the assumption of Egoroff's theorem, for each eta greater than 0 and delta greater than 0, there is a measurable subset A of E and an index n for which mod of Fn minus f is less than eta on A for all n greater than equals to n and measure of E minus A is less than delta. Okay, that means under the assumption of Egoroff's theorem means what are the given condition of Egoroff's theorem? Consider that all condition. That means E is a set which has finite measure, and second condition is what? Fn is a sequence of measurable functions on E that converges pointwise to E to the real valued function f. Okay, these are the condition which we have to consider. Okay, now under this assumption, see what we have to show. Under this assumption, we have to show there is some eta greater than 0, that is positive eta and delta greater than 0. There is a measurable subset A of E. There exists a set which is subset of E, and for that set an index n for which modulus mod of Fn minus f is less than eta on A for all n greater than equals to n. For all index, after that n, capital N, difference between all terms of the sequence Fn and f should be less than eta and measure of E minus A is less than delta. Okay, so proof, consider, let us see the proof. Given that measure of E is less than infinity, that is A has finite measure, okay, and Fn be a sequence of measurable function on E that converges pointwise on E, okay, to the real valued function f. Now, see, for each k, the function f minus fk is properly defined. Yes, it is defined. Okay. Then since f is a real valued function and it is measurable, given that f is a real valued function and it is measurable function, therefore the set x belongs to E, mod of f of x minus fk of x is less than eta is again a measurable set since your f is measurable and f minus fk is properly defined. Okay, that is why this set is measurable set. Again, we know that the intersection of countable collection of measurable set is measurable. Okay, it is therefore the intersection of all the set is again measurable. That means we have the set En, which is written as x belongs to E, such that mod of f of x minus fk of x is less than eta for all k greater than equals to n. After that n, there is some index n. For after that n, all set all the difference between f of x and fk of x is less than all terms of that sequence is less than eta. Okay, which is again measurable set. Okay, then En runs from 1 to infinity is an ascending collection of measurable sets, and E is equals to union of En, right? Therefore, Fn converges pointwise to F on E. Okay, therefore, by continuity of measure, we have measure of E is equals to limit n tends to infinity measure of En. By definition of continuity of measures, we will have since and what we have given measure of E is less than infinity, we may choose an index and for which measure of En is greater than measure of E minus epsilon, right? What is given? Measure of E is less than infinity, that is finite measure. Therefore, we choose an index for which that measure of that set En, that particular n, is greater than measure of that E. As we subtract that some epsilon, there exists some epsilon. If we subtracting that epsilon from measure of that set, then that measure of En should be greater than this term. Okay, so we define A is equals to En, and hence by accident property we have measure of E minus A is equals to measure of E minus measure of A, which is equals to what? Measure of E minus what is value of A? It is En. It is En. So it is measure of E minus measure of En, and this whole term is less than epsilon. Okay. Now, by choosing this is our proof of this theorem with lemma, which we have to prove. Okay. Now, if we choose, okay, this completes the proof. Now, see the proof of Egroff's theorem. Now, what is Egoroff's theorem? See, this is our statement of the Egoroff's theorem that E has a finite measure, and the condition is that Fn is a sequence of measurable functions on E that converges pointwise to E. Okay, to the real value, the sequence of the sequence converges pointwise to the real valued function on that particular set E, which is measurable. Okay, then what we have to show, there exists a closed set. Now in the lemma we have shown just there exists a subset of the A, which is subset of E, and on that set that sequence converges. Okay, this is simply statement of uniform convergence. Fn minus f less than eta for some eta, and for after that n, capital N, for all terms of that sequence Fn, this condition is satisfied. That means that sequence is simply uniformly converges. Okay, now here we have to show that on that closed set F, that sequence tends to that real valued function F uniformly. Okay, given that that sequence converges to that function, real valued function pointwise, and we have to show that that tends to that function again uniformly on that particular closed set. Okay. Now see. Proof of the Egoroff's theorem. Given that measure of E is less than infinity and Fn be a sequence of measurable function on E that converges pointwise on E to the real valued function here. What we have to show, then for each epsilon greater than 0, for each epsilon greater than 0, there exists closed set F, which is subset of E, for which Fn tends to F uniformly on that capital F. Okay, and second condition is measure of E minus F is less than epsilon. Okay. See, to prove this theorem, let us take a natural number, any natural number. Okay, see, for each natural number n, let an be a measurable subset of E, and n of n is an index. Keep in mind, your an is a measurable subset of E, and for that set, we have taken an index n of n, which satisfy the condition of the preceding lemma, that is the condition of previous lemma which we have seen. What is that lemma? This condition. We have choose a set an and the index n of n which satisfy these two conditions. Okay. And preceding lemma with delta, we choose here delta is equals to epsilon upon 2 raised to n plus 1 and eta is equals to 1 by n. So the conditions will write measure of E minus A, which is less than epsilon upon 2 raised to n plus 1, which is value of our delta, and second distance between mod of fk minus f is less than eta, that means it is 1 by n, okay, on an for all k greater than equals to n of n. This is for particular index. This is your equation second and this is your equation first. Okay. We define a set A is equals to intersection entrance from 1 to infinity an. Then by De Morgan's identity, the countable is by we are using three properties here together. Okay. So De Morgan's identity is the first property, second is countable subadditivity, and third subadditivity of measure, and that equation first. By using these three together, we have the equation which is C. Measure of E minus A. By using this measure of E minus A is written as measure of union entrance from one to by countable subadditivity is written as measure of entrance from 1 to infinity E minus A, but again which is less than equals to summation entrance from 1 to infinity countable subadditivity measure of E minus an, right, and which is less than summation entrance. Why? Because this total term is less than epsilon upon 2 raised to n plus 1, and we are varying n here over this term. So it is entrance from 1 to infinity epsilon upon 2 raised to k plus 1, sorry, it is 2 raised to n plus 1. Okay, it is 2 raised to n plus 1, which is equals to epsilon by 2. If you solve this sum, then you have your first epsilon is equals to, sorry, n is equals to 1, then this term is epsilon upon 4. Again you are vary in this way, 2, 3 by, then it is epsilon upon 8 and so on. So it is first term is epsilon by 4 and remaining terms are tends to 0. Okay, as denominator tends to infinity, that all that term tends to 0, so your final addition is epsilon upon 2. You can solve it by geometric series also. Okay, so it is, so this will be this will be your epsilon by 2. Okay, now we claim that Fn converges to F uniformly. That means we have shown here measure of E minus A is strictly less than epsilon by 2, and this is our first part of the theorem. Now it remains to prove that sequence tends to a real valued function F uniformly. Okay, now see, we claim that Fn converges to F uniformly on that set A. Let epsilon greater than 0. Choose an index and not such that 1 upon n naught is less than epsilon. We have choose the index of that sequence, any index of from that terms of sequences, that is n naught, such that value should be 1 upon n naught should be less than particular epsilon, which we have chosen already. Okay, so by equation 2 we have, see, what is our equation second? This is equation second. Mod of fk minus f is less than 1 upon n naught on an for all k greater than or equals to n of n. Okay, so now we write this equation in this way: mod of fk minus f is less than 1 upon n naught on a n naught for k greater than or equals to n of n naught. Just we have replaced that n by n naught here. Okay, however, A is a subset of A n naught and 1 upon n naught is less than epsilon. Therefore, mod of fk minus f. Therefore, mod of fk minus f is less than epsilon on A for k greater than equals to n of n naught, and therefore Fn converges to F uniformly on. See, this is what, this is our definition of uniform convergent sequence. They have epsilon and the difference between any two terms after that n of n naught should be less than epsilon for all k. Okay, that means that sequence tends to F uniformly, and hence the proof of the theorem sorry is that sequence tends to uniformly on A. And now we have the second condition is once A is less than epsilon by. Now see by theorem, by using this theorem, let A be any set of real number which is from chapter first. Let A be any set of real numbers let A be any set of real numbers, then for each epsilon greater than 0, there is a closed set here containing E for which epsilon of E minus outer measure of E minus F is less than epsilon, and therefore we may choose closed set here containing A for which measure of A minus F is less than epsilon by 2, and this completes your proof. Now see the next proposition. C proposition. Let f be a simple function defined on E, then for each let f be a simple function defined on E, then for each epsilon greater than 0, then for each epsilon greater than 0, there is a continuous function g on R and a closed set F contained in E for which f is equals to g on F and measure of E minus F is less than epsilon. Okay, that means what is given? That function f is a simple function. That means that function takes finite values and it is measurable, which is definition of your simple function. Okay, that function should be take finite number of values as well as that function is measurable. This is your definition of simple function. Okay, now define for each epsilon greater than 0, there is a continuous function g on R. We have to show the existence of continuous function g on R and closed set F contained in E for which f is equals to g on F and measure of E minus F is less than epsilon. Okay, so see the proof. First we write given condition and then write the proof. Okay, and let a1, a2, a3 and so on a1 be the finite number of distinct values taken by the function f. See here, a1, a2, a3, an are the finite number of values. Why? That is taken by f, and all values are distinct because your function f is a simple function. And simple function takes take finite number of values. Okay, taken by the function f and let then be taken on sets. These values are all values are distinct. Then this function takes these values on the set a1, a2 and so on an. That means where a1 from a1, a2 from a2, a3 from a3 and so on an from the set e respectively. Okay. Therefore the collection ek is a disjoint collection since ek is a disjoint. Same using the theorem let E be any set of real numbers then for each epsilon greater than 0 is a closed set F. Again using the theorem from our first chapter. Closed set F containing E for which epsilon of E minus F is less than epsilon. We have closed set. So for this collection we have the closed set F. Okay, that means this is what E being a set of real numbers which is measurable. And for any epsilon greater than 0, there is a closed set. There exists a closed set such as containing E. And for the closed set epsilon of that set satisfy the condition epsilon of E minus F is less than epsilon. Okay. Now here we have a closed set. We can choose the closed sets for any such that for each index k, one is greater than equals to k is greater than x. For all index, we can choose the maximum value such that a1 and s epsilon e2 and so on. And this is the definition of measure of ek minus ek by using this theorem. Measure of ek minus ek epsilon. Okay. Then f is equals to ek is from fk, being the union of finite collection of closed set. If we take a set of k, then these k's are finite because k vary between 1 to n. Okay. Then this is a union of finite collection of closed set. Closed set is a closed. This collection is closed. Therefore, k is closed. K is closed. Since ek given from T is a disjoint, therefore measure of E is closed. Difference from 1 to n ek minus k, which is equals to summation k times 1 to ek minus k, and that is less than epsilon y because equation of ek minus k is less than epsilon y with that condition, which is less than epsilon y. Then height is written even minus n minus epsilon 1 to epsilon 1 to epsilon 3 and so on into minus n minus epsilon epsilon plus summation k is so we have defined to take the values ak on one is less than equals to k is less than equals to since the collection of k since the collection of k is a disjoint g is from which is a continuous one since also function is continuous for a point x equals to y. There is another continuing x which is disjoint from the group set which is not equals to r of k. On the intersection of this set, the function is always constant but g can be extended from a continuous function to closed set. The continuous function or mod of r, the continuous function now see the Lusin theorem. We take the real value measurable functions of the एकच जॉईन आहे का कल्याणी आवाज येतोय कल्याणी आवाज येतोय का माईक
जास्त बॅकग्राऊंडचा आवाज आहे
तो तर येणारच आता सगळ्यांचेच लेक्चर चालू काय करणार दुसरे काही ऑप्शन्स नाही
लास्ट प्रिपोजिशन काहीच कळालं नाही मला
मॅम आवाज पण नाही आला आणि काहीच नाही कळालं
सांगते तुम्हाला परत एक्सप्लेन करते पण आता ते उद्याच्या लेक्चरमध्ये मी परत एक्सप्लेन करेन तुम्हाला लास्ट प्रपोजिशन पण ह्याच्यामध्ये असं आहे की हा तुमचा जो सेकंड चॅप्टर होता तो शेवटचा ल्युसिन जो थिअरम तो शेवटचा पॉईंट म्हणजे चॅप्टर आपला संपलेला आहे इथं ओके आवाज येतोय मी हा थिअरम तुम्हाला उद्या परत एक्सप्लेन करेन नोट्स याच्या कंप्लीट करायच्या आणि ल्युसिन थिअरमचा तो तुमचा होमवर्क आहे होमवर्कला तरी करायचं ल्युसिन थिअरम ओके जर काही अडचण आली तर फोटो टाकते ना तसं मी त्याचे नोट्स नाही काढले त्याचे फोटो टाकले ते तुम्ही अंडरस्टँड करून लिहू शकता थिअरम त्याच्यामध्ये फार काही नाही किती जण आहेत मला असं वाटतं कोणीच जॉईन वसुधा कोणी पल्लवी जगताप शैक्य विद्या ठीक आहे, मी हे प्रपोजिशन एक्सप्लेन करतो. थांबू आपण आता. तसं युट्यूबला पण टाकणारे व्हिडिओ असेल झालं इथे तर परत एकदा अंडरस्टँड करायचा प्रयत्न करा. नाही समजलं इथे तसं मेसेज टाका पर्सनल.